these two enthalpy factors also need to be taken into account. No? So that might mean that at the end the air has this enthalpy, but here you might have to consider that the enthalpy at the end is a little bit less or a little bit more. No? It's usually not a very big amount compared to the enthalpy of the air, but you have to include that little correction. Okay. Now the temperature of the product is something that is important to know. Because you see, for the temperature of the air is quite clearly controlled by this process. But what happens with the temperature of the product? Well, if the product was pure water, it would come out probably at the wet bulb temperature that corresponds to the enthalpy of the air. Because it would be evaporating in equilibrium like a wet bulb temperature. That's exactly what happens with a wet bulb thermometer. If, on the other hand, the product was completely dry, like a dry bulb thermometer, it will come out at the dry bulb temperature of the air. So the product will always be somewhere in between those two temperatures. So it's important to check. Remember that the temperature of the product has to always be in between the dry bulb temperature and the wet bulb temperature at the exit of the spray dryer. The exit of the spray dryer is at the bottom of the spray dryer. Remember? Big spray dryer, cone, little bottom exit in the side, thermometer. So it has to be in between. And the more dry the product is, the closer it will be to the dry bulb temperature at that point. And this, for products like sand or silicates or stuff like that, then it doesn't matter. You dry the hell out of them. Usually you dry them in countercurrent because you want to heat as much as possible. But for organic materials, extracts, things like that, you want exactly the opposite, and therefore you dry them co-current. And the place where they're going to be here depends on the water activity of the material. And if it's pure water, it would be here. If it's completely dry, it would be here. And depending on its water activity, it's going to be somewhere in between. So in the exam, I will tell you more or less how to find it somewhere there, okay? So right now in the spreadsheet that I'm going to give you in a moment, it's around 75% there, but it changes depending on the material. So this is a little bit problematic because to calculate this, you need to know the exit that goes out, the air that goes out, but to know the air that goes out, you need this. And this is, in this case, Excel doesn't do a very good job at the iteration, so it's better to do it manually. So you pick a number for this temperature. It can be wrong, it doesn't matter because it's a small factor. And then calculate, and then find what you get, and then the new number that you get, which is going to be a better number, put it in again, and then in 2 iterations, if you do it manually, you're done. I've done it like 157 times, and every time I've done it in 2 iterations. I've never had to do it 3. Usually works, okay? All right. So that's how our instrument, that's how our machine works. That's why we get a particular temperature of the product. Not because it does iterations, there's a little gremlin in there doing iterations all the time. It's because this simply reaches an equilibrium with the exit going out, no? With the air going out spontaneously. No? We have to do the iterations because we are not undergoing the process, fortunately. So that's what determines that, and therefore determines how whether this line is going to be lower or higher. So when we are going to compare, when we're going to try to understand that how our machine behaves, then we are going to have to understand how the simple action. We're gonna we in terms of control, we really did basically 2 things there, right? We either change the temperature in the little button, or we change the knob there, right? Those were the 2 basic things that we controlled. Most of the things we measured. So now you are an engineer, you're going to have this instrument, this machine there, and you're going to be asked to design a process, basically. Decide what numbers to put there to try to get something, right? So you have the experience of having operated the instrument, the equipment under different conditions, of having done mass balances, energy balances with actual product in the equipment, having thought about it. And now what we want is that you see it again with a deeper kind of perspective, which is really understanding. So that if you were to use it for a particular task, right, if you were commissioned by someone to do something, okay, go make this stuff. What would be the best way to do it, right? And you recommend, based on this sort of thinking process, some good set of processing parameters. And it's very possible that there is not like a single answer. No? There is like a region where the answer is okay. More than getting an exact answer, what we would like to see is that you can clearly justify your answer from the point of view of explaining to us the mechanisms that are here and how you saw this happening when you were doing your lab, that when you did this, you observed that, and here is the theory that underlies it, and here's how I observed it when I did it, and that's why I think it's going to behave like this, and here's my calculation to show you how that happens. And you're going to have your spreadsheet organized there. This is what we would like you to be able to do in this question. It's kind of interesting, and I expect that you're going to have a nice, perhaps a piece of paper, or you can do it in whatever you like, no? It doesn't have to be paper. You can, well, paper is nice, it's kind of light. No, don't do it in a stone. But something that you write, but if you have one of those things that you can write on it, you can do it, no? And then submit it. Any medium you like, you can do it. And then one thing that I'm going to ask you, I'll show you in a moment, how to connect this with the spreadsheet. So what you can be doing here is you can be putting little numbers like this, 3 for example, 5. And then in the spreadsheet, you have the same number, and this is connected to the spreadsheet, right? That way it's easy for us to follow what you did by hand, connect to the spreadsheet. You don't have to redo it or whatever, no? So I'll show you in a minute how these kind of things can be done as well, no? Questions until this point? Okay, so I think this is more or less kind of closest sort of look. There might be other things that pop out when we are doing when we're looking at the spreadsheet, but I think it kind of encloses most of what we have to learn about this thing. Okay? Any other questions? There's other few parts that I have not included very much here. For example, the drying of the droplet, you know, and the residence time, and the 2 sections of the drying. The first section happens when the droplet behaves almost as if it's a droplet of water that is shrinking, and it reaches a critical size, and then after that is the internal diffusion of the water vapor through the fixed diameter of the droplet, and that is something that also affects the performance of the spray dryer. However, it would take me more time, me and you guys, to build that into the exam, to actually be able to include it, no, in a quantitative way. You might be asked to explain how would that affect these kind of calculations, because it's not included here, so some kinetic aspects are not included, no? Okay. Let's then switch to this.